This video is just to introduce the concept of how we will find the domain given the equation of a function. And remember, domain is just a way of saying what are we allowed to plug in for x that won't break any rules. So one rule we don't want to break is that we cannot divide by a zero. So if we have a non-zero value and we're dividing, this cannot be 0 in the denominator. The other rule that we have to be careful of is that we're not going to take any even roots of negative values. So if you have a square root or a fourth root or anything like that, then whatever is underneath there cannot be negative. And so let's go ahead and take a look at how that would work in the following 4 examples. So the first one we have, for part A, f of t is equal to the square root of 5 minus t. So this 5 minus t is what's underneath the square root, and we basically want to say that cannot be negative, but instead of saying it cannot be negative, we're going to say it has to be greater than or equal to 0. It's fine to take the square root of a positive, and it's fine to take the square root of a 0. So those are all okay. It's just the negative values that are not. And if we, for example, add t to both sides of this, we get 5 is greater than or equal to t. In other words, t has to be less than or equal to 5. So as long as we have t values that are less than or equal to 5, when we take the square root of 5 minus t, we're taking the square root of a positive number or of a 0. The next part we have for part B, g of x is 1 over x plus 2. And so for this one, the issue is that we're dividing by something where there's a variable down there. And so what we have here is that the x plus 2 part cannot be 0. So the way I like to write that is x plus 2 not equal to 0. And you can kind of treat it just like an equal sign. X cannot be equal to negative 2. In interval notation, that looks like negative infinity up to negative 2, and then I use the round end of the interval notation to show we're leaving out negative 2, union negative 2 to infinity. So this is our way with interval notation to denote everything except for negative 2. And just to pop back to part A, if I wanted to do that in interval notation, t is less than or equal to 5 would look like negative infinity up to 5, and then the square bracket to denote including the 5. All right, let's skip ahead to part C. For part C, we have 2 different issues. One is that the square root of x plus 1 cannot be 0. And the other is that the x plus 1 cannot be negative. In other words, has to be greater than or equal to 0. So this sort of combines my 2 A and B sort of issues. So if I solve this second part, I get that x has to be greater than or equal to negative 1. However, if I use the negative 1 itself, you'd see how in the denominator we would end up with a square root of 0, which would mean we're dividing by 0. So instead of it being x is greater than or equal to negative 1, when we combine the 2 issues, that turns into just x has to be strictly greater than negative 1. So for this one, we have open parentheses, negative 1, comma, infinity for my interval notation. And that's just because that square root's in the denominator. Sometimes people wonder, what about the x minus 3 in the numerator? Well, if x is 3, we end up with 0 divided by a non-zero value. So that's just a 0 for the function. It's not a domain issue. Our last one, notice that we don't have any square roots. We have y equals x squared plus x minus 16. No square roots in sight, no variables in the denominator. This is actually a polynomial, and it has domain all real numbers, which we can write a few different ways. We can write all real numbers in words. We can write that capital R with the double line, and we can also write interval notation, negative infinity to infinity.